Okay, let's start with the Chapter 6 review. Question 1, 2, and 3 is what type of bond is formed between atoms of calcium and fluorine? And then 2 is what type of bond is formed between an atom of nitrogen and an atom of hydrogen? And then what type of bond is formed between two atoms of chlorine? And the first thing that you have to remember is that, I got to grab a pen. You have to remember that if the electronegativity difference is less than or equal to 0.3, this is called it's called a non-polar covalent bond. And what that means is a bond, like let's say we have atom X and atom Y, and they're bonded. A polar bond is one of the atoms. If one of the atoms wants electrons more than the other atom, they move towards the atom that wants them more, and that's the atom with the greater electronegativity, setting up this little tiny, if you think of it like a pole magnet, where this side has a partial negative charge and this side of the bond has a partial positive charge. And this only happens if there's a huge electronegativity difference. And in calculus, the symbol for partial is the Greek letter delta. So baby delta. You're used to capital delta for slope is change in y over change in x. But this is a little tiny shift and then a partial positive charge. If it's a small difference in electronegativity, less than a difference of 0.3, that doesn't happen. You don't end up with two poles. Dipole, di means two, poles mean a positive side and a negative side, like a bar magnet. Okay, that's neither here nor there. So then, well, just kind of a quick explanation, so if you remember why this matters. Then coming over here, if the okay, what'd they do? Sorry. Sometimes I push this weird thing on the side of my pen and it goes crazy. If the electronegativity difference is less than 2, but greater than 0.3, and by the way, we're using a chart, a different chart. It's a chart from the book. It's only good to one place. Then we say the bond is polar covalent. They still share. The two atoms still share. There's not a transfer, but it sets up this magnet idea. Now, the interesting thing is if the electronegativity difference ends up being greater than or equal to 2, that is the point at which there's no sharing, that the atom that wants electrons more is strong enough to actually take or capture the other atom's electrons. It tends to be, these bonds tend to form between groups 1 and 2 and group 17 and 16. So 1 and 2 want electrons the absolute least. Groups 17 and 16 want electrons the very most. And when this happens, it's ionic. Okay, so now that's a little backstory. Now, if we go up to the actual problem, I'm going to come back up here. What type of bond is formed between atoms of calcium and fluorine? You have to go to your chart on the back, and if you look right here, I don't know if you can see me doing this, but fluorine has an electronegativity of 4.0. Now, on your old chart, it was 13.98. It just, for the sake of the final, we made this a little simpler. And then calcium is 1.0. And so this actually, sorry, I do want to come back to this problem. This ends up being, so I'll just do it down here. It ends up being that because the electronegativity of fluorine is 4.0, that's the absolute highest, and calcium is 1.0, and then add absolute value of electronegativity difference. Difference means subtract. So 4.0 minus 1.0 is 3.0, and obviously 3.0 is greater than 2.0, and so this bond is ionic. And calcium's in group 2 and fluorine's in group 17. And calcium is actually, calcium's only 1, fluorine is 4. Fluorine is strong enough to take the electrons away. Okay, sorry, I had to unplug the phone. Okay, next one. Okay, how do I do this? Sorry. So then I'm going to push enter. Oh no, I could do this. Coming back to me. What type of bond is formed between nitrogen and hydrogen? So I come here. Um, you can see right here, nitrogen is 3.0 and hydrogen is 2.1. So I'm going to go back. And so if I look on the sheet, you'll see that the electronegativity of nitrogen is 3.0 and hydrogen is 2.1. And so if you calculate the electronegativity difference, um, it's 3.0 minus 2.1, which is 0.9, which is greater than 3 but less than 2. So this is a polar covalent bond. And then next question is two atoms of iodine, which is going to be nonpolar covalent, but let's look. Um, iodine is 2.5. Um, it doesn't even really matter what it is, it's going to be the same. But basically, this question is asking if you have I, and they both have an electronegativity of 2.5. Neither one of them is, they have exactly the same strength. Um, they both want electrons the most. The difference between them is 0.0, because remember, one decimal place, one decimal place. That's less than 0.3. And so this is actually a non-polar. Non means it doesn't set up the positive pole and negative pole. So this is a non-polar covalent bond. And actually, some books call this one, when the electronegativity difference is 0, some books call it a pure covalent bond. All right. So those are pretty easy, but it's good to do this review because you have to learn, okay, the only thing you're getting on your final is anything on these sheets that are attached to final. This stuff, we're going to use this stuff next. And so you got to also review the concepts, but also learn how to access the information for your final. So then question says, which type of bonding is characterized by the transfer of valence electrons? That is ionic, because what happens is if there's a huge difference in electronegativity, the metal, which has the low electronegativity, actually transfers. So for instance, in example 1, calcium, which has an electronegativity of 1, and fluorine with 4, when they connect, calcium actually gives one of its electrons to fluorine, because fluorine wants 1, so it can look like neon. Calcium actually gives away 2 electrons. So you always find that when calcium's in compounds, it will always bond twice, because it gives 1 electron to this fluorine and 1 electron to this fluorine, setting up a +2 charge. So now it gets to look like argon, and then this guy gets to look like neon. But anyways, the only thing you need to know is ionic. And sharing valence electrons is co for sharing, and valent. So what type of bonding is characterized by the transfer of valence electrons? Ionic bonding. Remember, bonding is just how we explain how atoms connect. And then this is covalent bonding. All right, next question. What is electronegativity? It is, I'll just define it for you. Electronegativity is the relative tendency of an atom to attract electrons to itself when it is bonded to another atom. And so that's like when calcium is connected to fluorine, the fluorine is attracting the electrons to itself, and that's how come it can pick up a bond. Okay, this was a really important concept, so let's take this slow. There's a lot of questions on this. So first thing, when you're drawing a molecule shape, you do what I call the octet rule prediction. And so you draw this molecule, which is made up of 4 different atoms, where every atom is connected to every atom with a single bond, and that every atom in your picture has 8 electrons in its valence shell, except for Habib. Watch out for Habib, because they're the ones, hydrogen wants 2, beryllium wants 4, boron wants 6, every other element wants 8. So if I do this, and I always just put them evenly spaced, turns out it doesn't look like this anyhow. So this sulfur right now has 2, 4, 6, so I got to put 2, and then this guy has 2, so I got to put 6, and this guy has 2, and I got to put 6, and this guy has 2, and I got to put 6, and I'm not going to draw the circles, but in my picture, 8, 8, 8, 8, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. ORP is 26 electrons. VE, however, is 24, because I'm going to swing back over here and show you that sulfur and oxygen are both in group 6A right here. So 18 or 8, 17 or 7, 16 or 6. And so sulfur has 6, but then each of the oxygen has 6. And so when I do 6 plus 6 plus 6 plus 6, I get 24. And if you'll notice, ORP is greater than VE, meaning we have too few valence electrons. When that happens, there's extra sharing. And so one of these bonds, it doesn't matter where you put it, one of these bonds becomes a double bond. So this sulfur, 2, 4, 6, 8, no dots. These dots are gone. And then 2, 4, 6, 8. So this oxygen used to have 6 dots, but now it has 4 dots because of the double bond, but these two still have 6 dots. And if you check, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, ding, ding, ding. This ends up being an AB3 type, because A is the central atom, which is the sulfur. B is how many letters or other atoms connect to the middle atom, which is 3, 1, 2, 3. And E is how many dots are on the central atom. And once we got rid of these dots, there's gone. And if you look over here, because I don't expect you to memorize this, but an AB3 is trigonal planar. You have to learn how to use this sheet. These are the shapes you're responsible for. And so you can see on here that AB3 is trigonal planar. And so this is how I'm filling out where it says type and shape. This is trigonal planar. And that it takes care of that first row on your review thing. All right, so next slide, NF3, same thing. There's no Habib, so you put the N in the middle, and you put the F's around the outside. I just do them evenly spaced. 2, 4, 6. This guy needs 2 dots. This guy has 2, it needs 6. This guy has 2, it needs 6. This guy has 2, it needs 6. And then 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. ORP is 26. VE is also 26 because nitrogen's in group 5 and fluorine's in group 7. And again, I probably should do this. Let's go up here. This is how this works. This is group 1, 2, 3, 4, 5. There's nitrogen in group 5. 6, 7. There's fluorine in group 7. So on this chart over here, 13, 14, 15, 16, 17, 18, it's the last number. So 18 is 8, 17 is 7, 16 is 6. So that's how the valence things go. But 3 times 7 is 21, and 21 and 5 is 26. And because ORP is equal to VE, this is a C left example because our picture is correct. You can see that this is an A, nitrogen is the A, B3. But in this case, we do have a pair of unshared electrons in the central atom. And if you go there, this isn't trigonal planar. AB3 is trigonal planar. This is trigonal pyramidal. And again, right here, you got to learn how to use this. AB3E1 is trigonal pyramidal. All right, next slide, XEBR4. So I'm going to do this. I'm going to put the BRs evenly spaced. I'm kind of making it look like a plus sign. Sometimes I make it look like an X sign. Doesn't really matter how you draw it because how it looks in 2 dimensions is not how it looks in 4 dimensions. Anyhow, it just helps us get the type. Okay, so all the bromines have 6. Xenon has 6. There's no hydrogen, beryllium, or boron. If I count 6 and 6 and 6 and 6, 6 times 4 is 24, 26, 28, 30, 32. ORP is 32. VE is 8. I'll flip over in a minute, but I'll show you that xenon is a noble gas. It's in group 8. And then 7 plus 7 plus 7 plus 7. 28 and 8 is 36. So I'm going to flip over here quickly and show you that xenon right here is in group 8. And is it fluorine? Whatever it is. There's a halogen in group 17. Actually, it's bromine. But still, bromine is in group 17, which means it has 7 valence electrons. But what happens is this time, ORP is actually not too big, but ORP is too small. And that means, I'm going to go up here and switch colors because I'm too lazy to redraw this. I have to take this original sketch, and the difference between 32 and 36 is 4. I have to add 4 dots. And this ends up being A for xenon, B4 for the 4-bromine, but E2 because this is one pair of dots and this is the second pair of dots. And if I go over here, you can see that AB4E2 is square planar, not planar, guys. Square planar. All right, next slide. CCl4. This one's actually pretty easy too. So I'm going to go C, Cl, evenly spaced. And so this has 2, it needs 8, so I got to put 6 dots. This has 2, it needs 6, I got to put, this has 2, it needs 8, I got to put 6 dots. This has 2, it needs 8, I got to put 6 dots. Carbon right here already has 8, so I don't have to add any dots. And if I do this, you'll see again that ORP is ORP is 32. It's just like the last one. 6, 6, 6, 6. 6 times 4 is 24. There's no dots here, so 24, 26, 28, 30, 32. But in this case, VE is also 32 because carbon is in group 4 and chlorine is in group 7, but there's 4 of them. 4 times 7 is 28, and 28 and 4 is 32, which means this picture is correct. And this is an AB4, and it is tetrahedral, and hopefully that's enough to help you do well on the test. So I'm coming back over here, and if you look here, it looks like AB4 is tetrahedral right there. Okay, next slide. Polar molecules contain a region of positive charge and a region of negative charge. Lists the 2 conditions necessary for a polar molecule. There's 2 of them. I did this to set you up for the next question. Condition 1 is the molecule must contain at least 1 polar covalent bond, which means going back, let me just go back to this one. These are the bonds, these lines, and so if you looked up these electronegativities, carbon and chlorine, and subtracted it, it would have to be bigger than 0.3 and less than 2. If this one is polar covalent, this bond, you look up xenon's electronegativity and bromines, and it has to be between 0.3 and 2.0, and there's 4 bonds here, and all you need to have is 1, 2, 3. Again, you have to check to make sure it's on the interval, and then right here 1, 2, 3, and single bonds and double bonds work the same. And so it has to have at least 1 polar covalent bond. And here's the tricky part too. These bonds can't be arranged symmetrically, because if they're symmetrically arranged, the shifts cancel. So like, let's say I have an AB2. Well, one shift goes this way and one shift goes this way, and the shifts cancel. And so you don't end up with a molecule with a region of positive charge and a region of negative charge. Now, if these bonds can't be arranged symmetrically, so sometimes I say, instead of that, the bonds can't be arranged symmetrically, I say the bonds must be arranged asymmetrically. Now, the toughest part, and I actually wrote it on the other part where I just gave the answers, on this chart, you're going to have to memorize that if the 1, 2, 3, so if they don't have an E in them, if they don't have an E in them, they're symmetric. So AB2, AB3, AB4, AB5, and AB6 are symmetric. Now, there's two other ones that are symmetric. This is square planar because squares are perfectly symmetric. I'll show you in the picture. And then the other one is if this linear is asymmetric, this linear also has to be, if this linear is symmetric, this linear has to be symmetric. So going back to this, what I need to say is, and I wrote it on your review guide, AB2 has symmetry because a line is very symmetric. AB3, which is is trigonoplanar. AB4, AB5, AB6, AB2, E3. This is the linear. And then just keep in mind lines are symmetric. And then AB4, E2, which is square planar. Let me go back to this picture. This is what happens. This bond, this shift and this shift would cancel, and this shift and this shift would cancel, and this unshared pair and this unshared pair would cancel. And that's if you want to think about it that way. So now, having said that, I have now, I'm trying to get you ready. Which molecules listed in question 7 are polar molecules? So here's the thing. Let me just go back. Not this. AB3 is on the symmetric list. This one is not polar. This one is polar because AB3E, AB3E1, it has asymmetry, and fluorine has an electronegativity of 4, and nitrogen has an electronegativity of 3, and 4 minus 3 is 1, and that is greater than 0.3 and less than 2. This has symmetry, it's not asymmetric, and this has symmetry, it's not asymmetric. And so the only one listed in 7 that's polar is NF3, because it's AB3E1. That is an asymmetric shape. And the NF bond has an electronegativity difference of 1, which means it's a polar covalent bond. We have both conditions, at least one polar covalent bond. We actually have 3 of them. And they can't be arranged symmetrically, so they can't cancel. All right, which type of bonding is explained in terms of the electron C model? That's how we explain metallic bonding. So just know that there's a multiple choice question on this. The type of bonding that's characterized by the transfer of electrons is ionic, sharing of electrons is covalent, and the electron C model is metallic. So basically, metallic is what you get when 2 metals connect. Covalent is what you get when 2 nonmetals connect, and ionic is a lot of times, because group 1 and 2 and group 16 and 17 is when a metal and a nonmetal connect. All right, that takes care of 6. Now, on question 12 here, I'm going to go over here, or sorry, not question 12, but chapter 12. Now, I'm going to toggle down here. You got to learn how to do this. I don't know where your graph is. All right, I'm going to have to pause for a minute. I'm going to go back and hit pause, and I need to find that graph. I'm going to hit this. I'll put. Okay, I'm back. Sorry about that. I had to go. I thought I had this up. Um, when I flip back and forth, then I'm going to make reference to this graph. I made it smaller so that I'm trying to make it as big as I can so that you can see it. Um, yeah, so here's the deal. So we're going to come back and forth to this graph. Here's the first question. Remember on this, the first, actually, I'm going to minimize this. First thing you do is you underline the substance and you underline the temperature and you read the graph. So the substance is NH3 and it's 80. And you come over here and you find 80 and you find NH3, which is right here. Where does NH3 cross the 80 line? Right here, where this little plus is. And my I see about 14. So now the first thing I have to write down is 14 grams of NH3 will dissolve in exactly 100 grams of water. After you do that, you look for a water match. Does the problem say you have 100 grams of water? Yep. Yep. They match. When this happens, you do not have to do the factor label method. We're going to go like this. Factor label method / you don't have to do it. You have enough information to answer the question. Determine the maximum mass of NH3 that can be dissolved in 100 grams of water. The maximum mass is 14 grams. That's the answer to the problem. That's the most. The most it can hold at 14. It can hold 1, it can hold 2, it can hold 3, it can hold 7, it can hold 14 point, no, it can't hold 13.9. If you try to put in 15, 14 dissolves, and once it's on the bottom, undissolved. Okay, question 2. First read through. Substance, temperature, Ki, 10. Go to the graph. Ki, 10. Go to the graph. Ki is way up here, 10's right here. I see 137. Make sure that you see that. And then I come over here and I'm going to go back and grab blue, maybe. All right, so then what happens is 137 grams of Ki will dissolve in exactly 100 grams of water. Okay, then you look for a water match. It says 100 grams of water. We do not have to do the factor label method, okay? Now we have enough information to answer the question. Now the question is, if you put 113 in, is it saturated or unsaturated? And the answer to the question is unsaturated. And the reason why the answer to the question is unsaturated is because 113 is less than 137. It can hold 137. You put in less than 137, so the liquid's not full. You could even put in, they didn't ask this question, but there is, the 100 grams of water could actually even hold 24 more grams. But the question is it saturated or unsaturated? All right, next question. First thing you do is NH4Cl, 25 degrees. NH4Cl, 25 degrees. The very first thing you do is you read the graph. So NH4Cl right here, this curve right here, 25 degrees, so kind of halfway between. And I see 39. I don't know if you see 39, but by the way, on a multiple choice test, just pick the answer that's closest. So I see, oops, that was bad. I can grab an eraser. I'm going to come up here, grab blue again. Okay, so when I read the graph, I saw 39 grams of NH4Cl per 100 grams of water. Then I look for a water match. We do not have a water match. It doesn't say 100, it says 250 grams of water. You must use the factor label method. Now, this is the conversion factor. When you have to use a conversion factor, whatever came off the graph gets written down second, not first. What gets written down first is the number in the problem that you haven't used yet. So 250 grams of water is the number in the problem we haven't used. We used the 25 to read the graph. And then And I could put that over 1 if that bothers you. And then if this is grams of water, this is the 100 grams of water goes down, so it will cancel. Um, the 39 grams of NH4Cl goes up. If I do that on my calculator, when I was doing my key, I think I got something like 97.5. Don't quote me on that. But that's not the answer to the problem because this has 2 sig figs, this has 3, so the best answer is 98. Now, on a multiple choice test, let's say you read the graph at 38. You're not going to get 98, so you should pick the answer that's closest to yours. Okay, again, very first thing you do is you look KCl 15 and you go and you read the graph. The graph is here. KCl is this one right here, 15, way down here, and I see 32. Actually, when I just did it, I saw 31, but my key says 32, so I'm going to do 32 grams of KCl per 100 grams of water. And now, after you read the graph, now we look for a water match, and we don't have, it doesn't say 100 grams of water anywhere. This is not there. You must use the factor label method. And when you use the factor label method, this thing gets written down second, not first. The thing that gets written down first is the only number in the problem you haven't used yet, because you use that number to read the graph. That gets written down first, 23 grams of KCl. And now this is the conversion factor, but it has to be inverted because grams of KCl is on the top. So the 32 grams of KCl goes down. The 100 grams of water goes up. Grams cancels with grams. If you do this on your calculator and round to 2 sig figs, you get 72 grams of water. You get something like 71.6666. I don't remember exactly, but you have to keep track of sig figs. All right. Determine the maximum mass that will totally, okay, so last one on this one, KCl, 70, go to the graph, always read the graph first. Here's the graph, 70 KCl, I think I picked KCl so much because you did a graph on it. I see about 46. Oops. Don't want to do that. I want to do this. So you always read the graph first. You have 46 grams of KCl will dissolve in 100 grams of water. And after you do that, you look for a water match. You don't have one. It says 37 grams of 70 degrees Celsius water, or 37 grams of water. When that happens, when you don't have a water match, you must use the factor label method. And this number does not get used first. This number gets used second. The number that gets used first is the only number in the problem that you haven't used so far, which is 37 grams of water. And if we want grams of water to cancel, then the 100 grams of water has to go downstairs, and the 46 grams of KCl goes upstairs. Boom, boom. And if I do this, my calculator says, I'm cheating. I don't actually know what it says. But my key says 17 grams of KCl. All right, cool. Next one, totally different. Find the molarity. All right, so I'm going to take you over here. I think we're done with this graph. I think all of the graph problems are done. Yes, they are. So I am going to close this, and then I'm going to go back here, and then here is the molarity circle. It says that molarity is moles per liter. And the only thing I'm going to tell you is that moles, if they don't give you moles, they give you mass. Put it where the moles go, because moles is related to mass. Sorry, I said that backwards. Mass is related to moles by molar mass. So to do this problem, I'm going to draw this big circle. That's such a bad circle. And there's the T. And molarity is moles per volume in liters. Okay, so step one, I'm going to find the volume. Is it in liters? Nope. 750 milliliters. I'm going to slide it 1, 2, 3 times, this is 0.750 liters. Step 2, in the problem, if you're looking for molarity, I put my hand here and it tells me that I have to put moles on top of volume in liters. Well, I don't have moles, but I have mass. So, and I know that mass is related to moles by this cool concept called molar mass. It has both terms in it. Mass is related to moles by molar mass. And so what I'm going to do now is I'm going to put the 58 grams on the top, the 0.750 liters below. If I stop the problem now, I'd be in grams per liter. Nope, molar mass is not molarity is moles per liter, not grams per liter. So then I have to go to my ion sheet, which is right here, and I have to look up sodium, right here, sodium, Na+3, and then I have to look up nitrate. Nitrate is NO3 minus 1. And so then I have to say, okay, well, what is sodium nitrate? If sodium is +1 and nitrate is NO3 minus 1, sodium nitrate is NaNO3. And then if I hollow my periodic table, I'm going to do this down here to get out of the way. Sodium is 22.99, nitrogen is 14.01, and oxygen is 3 times 16. And if you do that, trust me on this, you will get 85.00 grams per mole. And because grams is on the top, the 85 grams goes down, the 1 mole goes up, grams cancels with grams. I'm now in moles per liter. I put this in the calculator and I will get 58 times 1 divided by parentheses 0.750 times 85 rounded to 3 sig figs. You will get 0.910 moles per liter, or the abbreviation for moles per liter is capital M. All right, again, step 1, make sure that the volume is in liters. It's not 500 milliliters. I'm going to slide it 3 places. 1, 2, 3. This is 0.500 liters. Step 2 was do what the molarity circle tells you. So here's the molarity circle. Remember I said that, what is molarity? It's mole per liter. Okay, now this time it says how many grams. So here's my hand. Now I'm going to put it up here, not because moles is grams, but because moles is related to mass by molar mass. And so the circle tells me to take the molarity they gave you in the problem, 0.375, but instead of capital M, we can't do that because that's an abbreviation. It's moles per liter. And then that gets multiplied by 0.500 liters. And this is like the titration problems. Mole per liter times liter is going to be moles. And then I don't know what Na2SO4 weighs, but it's pretty easy to figure it out because I got 2 times 22.99. And then sulfur is 32.06, and then oxygen is 4 times 16. And when I add these together and use the periodic table, apparently you get 142.04 grams per mole. But this one's interesting because the 1 mole goes downstairs. I should just wrote this down so I'm not so... the 1 mole goes downstairs, and the 142.04 grams goes upstairs. Moles cancels moles. This has 3, this has 3, this has 5. When I put that in the calculator, you get 26.6 grams. All right. Okay, an aqueous solution contains 225 grams of calcium chloride. Again, let me just do this first. I'm going to get ready for it. Calcium is +2, chloride is -1 on your ion sheet. Let me just show you. We should know how to use this by now. Calcium is +2, chloride is -1. And so you might as well get the formula because I'm going to need it later. It's CaCl2. Step 1, find the volume, 1,250 milliliters. Is it in liters? Nope. It's in milliliters, 1, 2, 3. So the first thing, 1.250 liters, 1.25 liters. Now remember, this zeros are not significant. It's not a final zero. After the decimal point, it's not a sandwich zero. So this has 3, this has 3. And then what does the molarity circle tell you? It tells you if you're looking for molarities, you put mass or moles in the top because mass is related to moles by molar mass, and then but the volume in the goes in the bottom. And so first step is you have 225 grams of calcium chloride, and it is dissolved in 1.25 liters. And the reason we're not done is because we're in grams per liter, and we need to get in moles per liter. So then I haul out a periodic table, and calcium is 40.08, and chlorine is 35.45. And when I do this addition on a calculator, I get 110, something like that. What do you get? 110.98 grams per mole. And because grams is on the top in the first set of parentheses, the 110.98 grams goes down, the 1 mole goes up, this cancels this. You're in moles per liter. If I do on the calculator 225 times 1, which I really don't have to do, I shouldn't have done that, 1.25 times, this is a 10, people, 110.98. The calculator says that the answer is 1.62 moles per liter, or 1.62 capital M. All right, and that's it for the first two. And I'm going to stop because I think that this, we're at 42 minutes. And I think if I go any further, I bet this file is going to be too large.